Hi teacher, we are the team 9, Mario Trejo and Marcos Campos, and we're going to talk about thermodynamics. So, what is thermodynamics? Well, thermodynamics studies the exchange of energy in its various forms. One of the main goals of thermodynamics is describe the transfer of energy. We have already described two processes as a transfer of energy, work and heat, and they are both connected to each other. As a thermodynamic system does work, it loses heat. When work is done on a system, it gains heat. So heat is converted to work and work is converted to heat. Together, the work and heat transferred into or out of the system represent the change in its internal energy, which, as you might recall, is the total kinetic and potential energy of all the molecules in the system. This idea that the change in internal energy is equal to the change in work plus the change in heat is so fundamental that is known as the first law of thermodynamics. So we can have an equation to use for analyzing problems. Rewrite the first law like this: the energy U, that is internal energy, of a closed system is equal to Q, the heat transfer to the system, minus W, the work done by the system. In other words, the energy cannot be created or destroyed, only transformed. Now, the second law relates to entropy. But what is entropy? The second law of thermodynamics states that the entropy or disorder of a closed system is always increasing. A solid system spontaneously evolves towards thermal equilibrium, the state of maximum entropy of the system. More simply put, the entropy of the universe only increases and never decreases. One way of thinking about entropy is a measure of disorder or chaos in the universe. The more entropy we generate, the less energy is left over to do useful work. A simple way to think of the second law of thermodynamics is that a room, if not cleaned and tidied, will invariably become more messy and disorderly with time, regardless of how careful one is to keep it clean. When the room is cleaned, its entropy decreases, but the effort to clean it has resulted in an increase in entropy outside the room that exceeds the entropy lost. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. The entropy of a system at absolute zero is typically zero, and in all cases is determined only by the number of different ground states it has. An important idea to note is the absolute zero may not be able to be achieved experimentally. This is because we know from the second law of the thermodynamics that heat will spontaneously move from a warmer body to a cooler body, so the object that you are trying to cool to absolute zero will be taking in heat from its surroundings. Despite this, absolute zero is an important theoretical concept. We learned about internal energy and two ways that it can be transferred by heat or by work. We know that heat is the form of energy that is transferred between systems or objects with different temperatures. Remember that measuring heat change is closely related to enthalpy, which we defined as the internal energy of the system plus the energy that is used to push the surroundings back and make room for its own pressure and volume and at constant pressure like we have here that works out to be exactly the same as the heat that's absorbed or released by reaction. Naturally, it could be very useful to know how much heat a chemical reaction absorbs or releases. A reaction which is exothermic enthalpy negative and results in an increase in the entropy of the system, entropy positive, will always be spontaneous. Consider the combustion of a fuel like ethanol in an oxygen gas in air. The products of the combustion reaction are carbon dioxide gas and water at temperatures above 100 degrees. This combustion reaction releases 1368 kilojoules of heat energy per mole of ethanol consumed in the reaction. We can represent the combustion of ethanol in a balanced chemical reaction as shown. The combustion of ethanol is a spontaneous chemical reaction because as the reaction proceeds from left to right, enthalpy is minimized because heat is a product of the reaction. Enthalpy of product molecules is less than enthalpy of reactant molecules. So enthalpy is negative. Entropy has increased. There are 3 moles of gas on the left side of the equation and 5 moles of the gas on the right hand side of the equation. Ethanol can be used successfully as a fuel because once the combustion reaction begins using a spark for instance to overcome the activation energy, it will keep going without any further help. And this is the definition of a spontaneous reaction. If the forward reaction is spontaneous, does that mean the reverse reaction is non-spontaneous? The reverse reaction would require carbon dioxide gas and water vapor reacting to produce ethanol and oxygen gas. When we reverse the chemical equation, we must also reverse the sign of the enthalpy change for the reaction. That is, this reaction will absorb 1368 kilojoules of energy per mole of ethanol produced. And this reaction is not spontaneous. It is non-spontaneous because enthalpy has increased, not decreased. The reaction absorbs energy, so enthalpy products greater than enthalpy reactants. Reaction is endothermic. Enthalpy is positive. Entropy of the system has decreased, not increased. 5 gaseous molecules on the left side, but only 3 on the right hand side. It's probably used as well that this reaction is non-spontaneous. In conclusion, a reaction will always be spontaneous if delta enthalpy is negative, is a exothermic reaction, and delta entropy is positive, entropy increases. A reaction will always be spontaneous. If delta enthalpy is positive, is an endothermic reaction, and delta entropy is negative, entropy decreases.
That's all for us. Thanks for watching and have a great day.